Go, Section 5, representing linear patterns. If you remember back to, I believe it was Section 2, we did the exact same thing we're going to do in today's lesson. So hopefully if you remember that, you shouldn't have much trouble with this. It's going to combine that with graphing and with a few other things that we did. Let's look at the first problem. This problem should remind you of back, and this is the lesson I'm focusing on, or talking about. Back when we rented, I think we rented a bicycle, and it said it charges you so much per hour plus an initial fee. This is the same type problems. If you can do those, then these are going to be easy to you. The first problem says a DVD buyers club charges $20 membership fee plus $20 membership fee and $15 per DVD purchased. Pull my pen up. Finish the table that represents this situation. Pull up my names. You get $20 membership fee, so you're paying that up front, plus you're going to pay an extra $15 for each DVD buy. So if you buy 0 DVDs, how much are you going to pay? Good job. $20. Everybody understand that? If you buy 1 DVD, you still have to pay the $20, but you've also got to pay $15 for that DVD. You're going to pay $35. Good. If you buy 2 DVDs, you're going to pay, I'll give you a second thing. I think I heard it. $50. Does everybody understand why? Two DVDs, $15 for each. That's 15 and 15 is $30, plus the $20 membership fee. If you join and bought 3 DVDs, you're going to pay $65. Next would be $80, and next would be $95. Let's talk about the process, because it's all about the process that we use for finding these different values. What if I wanted to buy 20 DVDs? What process would you use to figure out how much 20 DVDs would cost? It would cost $300 for the DVDs, and then an extra $20 for the membership. Good job. So you've got $320. What process did you use? How did he find the $300? There you go. That's what I was looking at. The process is an equation. You do 15 times X, 15 times the number of DVDs, plus the $20 membership fee. Before we talk about that, though, it says the constant differences in both the X and Y's tell us we have a linear relationship. Go back to, and again, we're taking all the stuff we've done in this chapter and putting it in one section now. A constant relationship. Do you remember constant differences? Do we have a constant difference with our DVDs up here? +1, right? Do we have a constant difference on bottom? We're adding 15 each time. That means that this is a linear relationship. Let's talk about what a linear relationship is. What is the root word of linear? Line. If you have a linear relationship, if we graph this, the graph would look like a straight line. You'd have dots that lie in a straight line. So constant differences in both the X and Y's tell us we have a linear relationship. This means if we graph the order pairs, it creates a straight line. Now again, it says what is an equation that represents this scenario. What I'm going to let this do, I'm going to let our DVDs be D. And let's let that be little d. And the cost, our total cost, be big C. The way that I'd write the equation that represents this scenario, the cost of our DVDs, and it's exactly what Mikey said, you go with the steps that you took. How did you find the different cost? It's pretty much it. The cost is equal to, say it again, Mikey, 15 times D plus 20. Because you're saying 15 times however many DVDs you buy plus the $20 membership fee. That is an equation that represents that scenario. Example 1. You've got the same type thing. Your homework is going to look just like these problems. It says the table shows the cost associated with an audio CD club that charges a membership fee. Write an equation to represent the pattern in the data. Let's see. Haley, can you look at this table? 0 CDs cost $21. 1 CD costs $31. 2 CDs cost $41. Can you look at that table and tell me how much money you're paying for each CD? $0 costs $21, $10. Good job. Does everybody understand that? If you're paying $21 for no CDs, $31 for one CD, you got one extra CD, paid $10 more. Two CDs was $41, you paid $10 more. Each CD you're paying $10 per CD. Does everybody understand that? Now what about this? Can anybody else look at the chart and tell me what the membership fee is? $21 membership. How did you know that? That's it. 0 CDs, you've still got to pay $21. Obviously, that's your membership. Write an equation to represent the pattern in the data. I'm going to do the same thing. We'll let our CDs be D and our cost be C. The cost for CDs is equal to, let's see, somebody different take a stab at this one. Dustin, you think you can get it for me? You're paying $10 per CD plus a $21 membership fee. How do you write $10 per CD? 10, not plus D. Think about it like this. If you buy one CD for $10, how much you pay? 10. What if you buy 2? 20. What if you buy 5? 50. How are you finding those values? You're multiplying by how many CDs that you bought. That's it. 10D plus 21. There's your equation. Any questions? $10 per CD plus the $21 membership fee. Does everybody see that it's just like the stuff we did before? It's pretty much exactly. The only thing that changes is you got that letter out front. And you could now graph it. When an equation is graphed and the resulting graph is a straight line, we call it a linear equation. We've done talked about that. Linear root word line. In every linear equation, there is an independent variable and a dependent variable. The independent variable, usually x, which in this case it wasn't x, is the variable that normally is on the left side of the t-table. So if you make a t-table, you know how normally you do x, y. This, whatever's on the left, is called your independent variable. Whatever's on the right is called your dependent variable. That's what this next paragraph says. When you actually graph it on a coordinate plane, your independent variable is your horizontal axis, your dependent variable is your vertical axis. Now let's talk about why it's called independent and dependent. Let's talk about the meaning of those two words. Dependent. Something depends on something else. Both of you are exactly right. Most, I would say probably all of you are dependent people because most of you aren't self-sufficient. You don't have a job to where you have to buy your groceries and food. You don't have to pay house payments. You don't have to do these things. Somebody else does it for you. So you're dependent upon who you stay with. Once you get older and get out on your own, a word that a lot of people use for that is independent. Okay, you're no longer dependent on something else. The same way here. X and Y, think back to our last section. When we graphed, we chose values for X. We plugged them in, and we got our Y values. Do you see that Y depended on whatever X was? That's the reason we call Y a dependent variable. And X is independent. We can choose anything we want to for X. It makes its own rules. X is independent, Y is dependent. Example 2, nearly finished. Before we do that, though, I want to give y'all some more examples of what we were doing before. Watch this. I want you to be able to take, because this is what your homework is going to look like, I want you to be able to take an XY table, 0, 1, 2, 3, 4, and I'm going to work about 4 or 5 more examples of these. 7, 9, 11, 13, 15. If I give you that, you should be able to, within probably 10 to 15 seconds, give me an equation for that XY table. Let me show you how to do this. Okay, so if we took this and we talked about, this is no longer talking about CDs and cost and all that, but we can think of it like that. What if we were still buying CDs? Well, let's look at this scenario. 0, 7, 1, 9, 2, 11, 3, 13, 4, 15. How much would you be paying per CD? For 0, you paid 7. For 1, you paid 9. You're paying $2 per CD. Does everybody understand that? $2 per CD. How much would the membership fee be here? $7. Good. Makes sense. $2 per CD plus the additional $7. So the cost, or in this case our Y's, Y is equal to $2 per CD. How do you write that? 2, in this case, our variable is x. 2x plus, what's the initial fee? There's the equation. Your homework looks just like that. Go ahead, Elizabeth. Okay, let's not start on our homework yet. Let's finish this and then we'll start on homework. No, we're still going through the lecture. Let's do some more. X, Y, 0, 1, 2, 3 is plenty. 9, 13, 17, 21. Okay. How much are you paying per CD here? $4. What's your initial fee? $9. $4 per CD. The Y is equal to $4 per CD. How do you write that? 4 per CD plus an initial fee of $9. Y equals 4x plus 9. Any questions? Does that make sense? Whatever the difference is, whatever that constant difference is how much you're paying for each of them. If you pay $4 for each, well, 1 it costs 4, 2 it costs 8, 3 it costs 12, 4 it costs 16. You're multiplying there. So $4 times however many you buy, plus you have to add on that initial fee. Let's do one more like that, and then I'll do one where it's going down like what Elizabeth was saying. X, Y, I'm going to trick you on this one. 1, 2, 3, 4, 8, 12, 16, 20. You're paying $4 per CD. Makes sense. What's your initial fee? Your initial fee is also $4, but you're saying, but it's got an 8 there. Is that your initial fee? That's how much you're paying for one CD. Not necessarily. You're paying. Well, let's look at any of the different cases. You're buying one CD. You just told me you're paying $4 per CD, right? $4 per CD. Well, if you buy one CD, you're paying $8. So the other $4 must be your fee. You could have also done it from 2 for $12. Two CDs cost $12. Well, those 2 CDs were $4 a piece. So that makes $8. So how much is left over for the fee? $4 still. Same way here. 3 CDs. That would be $12 if you did 3 times 4. Well, how much extra do you have over here? $4. That's your fee. So Y equals, what would it be in this one? 4x plus 4. Any questions? Now the one that Elizabeth was asking about actually goes backwards. 0, 1, 2, 3. Let's do 10, 8, 6, 4. These are a little bit tougher. You've got one like this on your homework. The initial fee, no problem. Right? It's 10. So it's Y equals something times X plus 10. But think about it like this. Go back to the problems that we worked before. How did you get how much you were paying per CD? You were going from 8 to 12, right? Which was plus 4, plus 4, plus 4. So this one will actually be a negative problem. And if you think about this one in terms of CDs, it's going to confuse you. But if you think about it as in terms of constant difference, what are you doing from 10 to 8, from 8 to 6, and from 6 to 4? You're going negative 2, right, each time? So you're going to say Y equals negative 2 times however many X's there are plus 10. Makes sense? It's the same thing, but instead of adding something each time, you're decreasing something each time. There's only, I think, one of those problems on your homework. There's 2? Okay. So here we go. Let's finish out. We got example 2 and example 3, and then we're finished. Example 2 says a passenger train averages 54 miles per hour. Write a linear equation that represents the distance traveled in a given time. Graph the equation for time 0 to 15 hours. Well, let's try that. Let's talk about what this right here means, because a lot of people don't understand it. Miles per hour. Okay, let's talk about what miles per hour means. If you're traveling 10 miles per hour, I know that's not very fast, but if you're traveling 10 miles per hour and you travel that speed for 1 hour, how far do you go? 10 miles. Does that understand what 10 miles per hour means? You're traveling 10 miles each hour. That's miles per hour. 10 miles per hour for 2 hours, you go 20 miles. 10 times 2. 10 miles per hour for 5 hours, you go 50 miles. That's what this problem's saying. A passenger train goes 54 miles per hour. Write a linear equation that represents the distance traveled in a given amount of time. If they give you a speed, 54 miles per hour, it is very easy to write an equation for that. I'm going to use D and T for distance and time. So, the distance we travel is equal to, if you're traveling 54 miles per hour, if you go 1 hour, you go 54 miles. 2 hours, 108. How'd you find that? You added 54 again, or you took, what about this though, 10 hours? How are you going to find that? 54 times 10. So you're going to take 54 and multiply it times the amount of time. 1 hour, 2 hours, 3 hours. There's the equation for traveling 54 miles per hour, how far you travel. 1 hour, 54, 2 hours, 108. Any questions? We got to graph it. Graphing it goes back to what we did Friday. Time and distance. Yes, sir. That's good. Whatever letter is over here by itself most of the time will be your dependent variable. Whatever letter you're plugging into will be your independent variable. Okay, back to the problem. It says to graph it for 0 to 15. What I'm going to do is put 0, 5, 10, 15. Let me explain this to you. A lot of people are having trouble with, what do I put over here? Because it was always 1, 2, 3, 4, 5 on our homework the other night. It doesn't matter what you put. You can put 1, 2, 3, 4, 5. You can put 0, 5, 10, 15. Listen close to that. You can put -2, -1, 0, 1, 2. It does not matter what your x's are. Why? What did we call x a while ago? What type of variable? Independent, which means it can be anything you want it to be. As long as you're plugging that in to find your y's. Can y be anything we want it to be? No, it depends on what x was. So let's take our equation. D equals 54 times t. If you travel for 0 hours, how far do you go? 0. It'd be hard to move in 0 hours, correct? If you travel for 5 hours, I'll give you a second to think about that. Try to do it without your calculator. Think about it. 54 times 5. What's 50 times 5? 50 times 5. 250. Now what's 4 times 5? 20. What's 250 and 20? 270. 54 times 10? 540. 54 times 15. Let's think about that. You multiplied it by 5 and you multiplied it by 10. Just put those together. 810. But we got to graph that. We have to graph somehow 0, 0, 5, 270, 10, 540, 15, 810. If you do not change your scale, there is not enough graph paper at Walmart to graph that, right? You're going to have to be taping stuff together and all sorts of stuff. You're going to have 810 boxes of it. Let's talk about scale. Let's talk about scale. You're going to have to somehow think about it. Be reasonable about it. Would you let each box with your... Well, before we talk about this, though, I skipped over this. Do you still have an x-axis and y-axis here? Trick question. No, you don't. Can you tell me what type of axis you have? I think somebody might have said it over here. You have a t-axis and you have a d-axis. You have a t and a d. You no longer have x and y in this problem. You have a t and a d. So your x-axis is now your t-axis. Your y-axis is now your d-axis. So here we go. 0, 0, 5, 270, 10, 540, 15, 810. Let's let our scale, what about our d-axis? Would you let it be maybe 5 for the d-axis? To where you say 5, 10, 15, 20, 25. How far up are you going to have to go? 810. Is 5 a good choice? No. 100 would be a good choice. 102. Let's let it be something even. You could let it be 102. Or 108 actually would probably be a better choice. Then you've got halfway marks and stuff. But what I'm going to do is, let's let it count 100. And look what I'm about to show you. If you put 100 here, 200 here, 300 here, 400, it might get crowded. You don't have to put all of them. If you just want to put every other one, the first line's 100, second line's 200. This line's 300, the next line's 400, 500, 600. You see what I'm showing? You don't have to mark every line to where it's not as crowded. Your t-axis, could you do each box counts 1? Sure, 15's reasonable. You could fit 15 on there. Would it be better to use something else? Probably. 5s would be a good choice. 5, 10, 15. First tick mark was 5. I didn't put the second one. The third tick mark is 15. The next one would be 20, and the next would be 25. So 0, 0, put you a dot there. That's the origin. 5, 270. So let's think about it. It'd be right below the 300 line. So we go to 5, and we go up to about right there. Would be pretty close. It's over halfway, because halfway would be 250. Then we got to do 10, 540, which is, let's see, 540. Here's, how much is this? That's 500. So a little bit below a half. Good job, Sean. And 15, 8, 10, you go to 15 and go up to 8 and a little bit above. Do you see it's a straight line? I'm going to put an arrow there. Think about this. And there's a lot of things that come into play here. I only put an arrow on one end of that line. AJ, explain to me why I probably just put an arrow on one end of it. Why does it not go forever in the other direction? Sean? Why does it start at 0? But, I mean, other graphs that we did went the other direction. Sandra, why does it... Because you can't go negative. What is T and D? What's T? Time. What's D? Distance. Can time and distance be negative in this case? No. So that's the reason I start at 0, 0. That's my starting point. Can I go further to the right? Sure. Can I go further to the left? No. So we stop it right there. Okay, last problem, example 3. And I really like this problem. Let's talk about it. It says, exercise physiologist suggests that a reasonable estimate for a maximum heart rate during exercise is no more than 220 beats per minute minus the person's age. Before I go any further, let's talk about maximum heart rate. I know it has possibly not much to do with math, but in this problem it does. Let's talk about what maximum heart rate even is before we even try to work this problem. Can anybody explain to me what is a maximum heart rate during exercise? No, I don't want a number. I want you to explain to me what it is. It's the fastest your heart can go, or it can go faster. But the problem is, if it goes faster than the maximum heart rate during exercise, you have might have some serious complications. Heart blowing up, whatever. Yeah, something might happen. Negative effects. So let me explain to you, and it's good to know. This is good health type things, and you'll be taking health before too long, I believe. So this will kind of get you a head start in health. When you're exercising, you have what's called a target range, to where if you go out and you walk around the block, and you never get tired, and somebody else goes and runs around the block, and they work out, they seem to be working more. Who's probably going to be burning the most calories there? The one running. Do you know why? Because if you can get your heart, do you notice when you run your heart? Do you notice when you run, your heart starts beating faster? If you can get your heart in that beating in that target range, you burn more calories. And that's the reason when you're exercising, a lot of people, you'll see them kind of taking their heart rate during their exercising. They're trying to get their heart rate in between here and here, that target range. Because if you're there, you burn more calories. And a lot of people don't know that, and a lot of people will go out and they'll just take their time, they'll just stroll along, they're just barely walking, they're not burning many calories. The best way to exercise is to get that heart rate up to the maximum, or to the target range. The top part of that target range is this maximum heart rate. You don't want to go over that, because under it, you don't burn calories. Middle of it, you're burning what you need to. Over it, dangerous. Yes, sir. How do you check your pulse? We'll talk about that after we finish. I'll show you how. So here we go. Let's work this problem. And this will show you what your maximum heart rate is, your dangerous point, your red line. Exercise physiologists suggest that a reasonable estimate for a maximum heart rate, which what we're going to call, what variable would you use for the maximum heart rate? M. Sounds like a good one. During exercise is no more than 220 beats minus the person's age. What's your other unknown there? The person's age. What letter are we going to use for it? P or A, either one. We'll call it P. Person's age. So M, the maximum heart rate, is equal to Finish that out for me. 220 minus P. That's how you find your maximum heart rate. 220 beats minus the person's age. Any questions? So if you were 10 years old, what would your maximum heart rate be? 210. If you were 20 years old, what would yours be? 200. You can plug in and you can find your own. It says write a linear equation to express the maximum heart rate in terms of age. We just did that. Graph the equation for ages 10 to 50. Let's do that. 220 minus P. M equals 220 minus P. Let's do us a XY. Well, XY axis. Actually, instead of XY, it's PM. Because the P is what you're plugging in, the M's are what you get. So we got P and M, and it says to find them for 10 up to 50. And I'm not going to find all of them. And this goes back to the question somebody had the other day. Why would I find all of them when I can just find, wasn't it you that asked me about the in-betweens, why do we connect it? Was that your question the other day? Instead of having to find 10, 11, 12, 13, 14, 15, 16, why not find 10, 20, 30, 40, 50, and then connect the dots? That way I didn't have to find 11, 12, and 13, because when I connected the dot, it included it. So 10 years old, you said, was 210. 20 years old was 200. 30 would be 190, 180, 170, patterns. It's all about patterns. Your p-axis, which is your left and right axis, and your m-axis is your up and down. Your p-axis, let's talk about the scale for the p-axis first. Each line counts 10, 5, either one. We'll do 10. First one would be 10, 20, 30, 40, 50, 60, 70, 80, 90. Your m-axis. This is a little bit tougher, and you're going to have to decide on your homework what to let your scales be. Your m-axis, 210, 200, 190, 180. Our highest one's 210. That's a good one. 20, 40, 60, 80, 100, 20, 140, 160, 180, 200, 220. Perfect. So let's see, a 10-year-old is 210, which would be, there's 200, halfway would be 210. A 20-year-old is 200, which is that mark. 30-year-old is 190, 180, 170, 160, 150. I went further than we had to. Now let's talk about, where would you draw arrows on this one? Would you? Because 0 would be 220. Can you go any further than 0? So let's start at 0. And does it go further than 90? Yeah, it actually does. How far does it go? I don't know. I don't know how long somebody's going to live. I believe modern day, the record's like 140 something. I mean, it's on up there. That's old. I don't know if I'd want to live that long. But anyway, there's your graph for this equation. Any questions?